Hello everyone, my name is Vinicius Kogo and I'm going to present our brief announcement titled Auditable Register Emulations. It is a joint work with Professor Alisson Bessani, and we both are from Lasige Faculty of Science of the University of Lisbon. The full version of our paper is available on arXiv, and in this work we have addressed the following question: how to extend resilient storage emulations with the capability of auditing who has effectively read data. So before I start to answer this question, I recall that most resilient storage systems are composed of any storage objects, which are, for instance, only read-write registers, and also that these systems usually employ information dispersal techniques like secret sharing and erasure codes. For instance, in some high-level write operation, when we want to write a value v in the systems, this write operation splits and converts the value v into n different blocks. And each one of these blocks is sent to a different object in the system. Also, interestingly, at the end of this operation, no base object stores the whole value v. When a reader wants to read data from these systems, he only needs to obtain tau different blocks of the same value to effectively read and recover the original value v. So back to the question, the original question, how to extend the resilient storage emulations with the capability of auditing who has effectively read data. So the extensions we foresee to audit this type of systems is to consider that we need to activate on each one of these objects a local log. Okay, so this local log makes these base objects pass from read-write registers to become loggable read-write registers. And also, it requires that every time a reader reads blocks from these objects, each object creates on its log a record with the reader identifier and the label of value v from which the block was derived from. So with this record, we can store the list of operations that each object has executed, and then a high-level audit operation can receive some of these logs and try to figure out and try to report what were the effective reads that have happened in the system. So basically, in the system, we have defined that if auditors receive at least a threshold number delta records with the same reader identifier and label of value v, then they can create an evidence of this read, of this effective read, and it will be used to report the operation. Okay, so given this whole system and these background concepts, we intend to define and identify the lower bounds to make resilient storage systems auditable, based on these metrics that we have been discussing. The tau blocks that a reader needs to recover the original value, the n objects that compose the resilient storage system, and also the threshold delta as the number of records that the auditors need to receive to then create evidence of the effective reads. So the system model that we assume in this work is that we assume an arbitrary number of client processors. This process can be writers, readers, or auditors. And these clients interact with a set of these n-based storage objects by invoking operations. More importantly, we consider that the high-level reads in our systems are fast. It means they finish in one communication round trip, so there is no communication among base objects, and the clients only do their request, the invocation, wait for the response. And also that audit quorums that will receive the logs from the base objects are available. It means that auditors will not wait the responses from all objects. They only need to wait from n-f objects. Additionally, the fault model we assume is that faulty writers and auditors can only fail by crashing. Faulty readers may be Byzantine, and faulty storage objects can fail in several ways. So basically, they can crash, omit their blocks to readers, omit read records to auditors, or record non-existent read operations. If we separate all these failures into two categories, we can say that the storage objects may fail by omission when accessing their blocks and may fail arbitrarily when providing their log records to auditors. Additionally, we assume that no more than F storage objects are faulty. We have identified, and this is common knowledge on auditability, that the properties that we need to accomplish auditable registers are the completeness and accuracy. So we have to support completeness as a means of protecting the system from readers trying to obtain data without being reported. So it means that every value V that is effectively read by a reader is reported by auditors. And also the system must support at least one flavor of accuracy to protect correct readers from faulty objects trying to incriminate in them. So we have weak and strong accuracy, and they differ on the value, on the sureness, on the value that they can report that as the reader having read. So in the first case, the weak accuracy only says that a reader that has never invoked a read in the system will never be reported by the auditors. And the strong accuracy goes beyond that and says that a reader that has never effectively read a value V will never be reported by auditors as have done so. Lately, we also consider that weak auditability is composed of the registers supporting both completeness and weak accuracy, and strong auditability is composed of supporting completeness and strong accuracy. The results in our model with the fast reads is that auditability is impossible if we assume that the number tau of blocks that our readers need to obtain to recover the value V, if this number tau is smaller or equal to 2f, then auditability is impossible. It is an interesting result because most resilient storage systems assume that this number tau is sufficient to be bigger than f plus 1. Okay, so when we have also want to support the weak auditability, we have identified and proved that weak auditability requires tau bigger than or equal to 3f plus 1 objects or elements, blocks, to guarantee then that the completeness and to guarantee that f faulty objects are not enough to incriminate a reader. And finally, when we are assuming that the system supports fast reads, strong auditability is impossible. Okay, so we have here an intuition on that proof, and I invite you to read the complete paper to better understand on why is it impossible. We have also evaluated some alternative models, and we have proved other results for these alternative models. First, when a reader signs his read request generically, so he does not say what is the value that he wants to read, and just signs the read request, it overcomes the weak accuracy lower bound and then enables the weak auditability with tau bigger or equal than 2f plus 1. Additionally, we have also identified that totally ordering the operations or using non-fast reads enables strong auditability with tau bigger or equal to 3f plus 1. These non-fast reads we assume as an operation, for instance, where a reader first reads metadata from the base objects to try to identify which is the value, the most up-to-date value that the system stores. And then when the client will send the request, it will request only to read that value, the most up-to-date value. And for that reason, it enables the strong auditability. And the best result that we have found is that combining non-fast reads with specific signed read requests. So as you remember, the non-fast reads enables one to learn first which is the most up-to-date value that the system stores. And then if readers sign the read request specifically for that value, then it enables the strong auditability with tau bigger or equals to 2f plus 1. Interesting, these results have practical implications. First, the idea of auditing resilient storage systems is feasible because many storage objects already support activating the log access. So we simply activate the log access and we can use it the resilient storage system using those base objects to support auditability. And it ranges from data-centric public cloud services like Amazon S3 to network file systems and local file systems. So any of these types of base objects, we simply activate the log functionality, and then we can have auditable register implemented on them. Additionally, other practical and existing resilient storage emulations need F to 2F additional objects compared to their original lower bounds to support this auditability that we focus on this work. And the reason is that they assume that the tau can be smaller than what we proved that is needed for auditability. But there is an interesting point here, is that requiring more base objects on these resilient storage emulations actually decreases their storage overhead, because having more storage objects allows us to store smaller blocks to support the same number of faults. So with this, I conclude this presentation and hope that have sparked interest in this topic and to read our full version of the paper. So thank you.